Hello there, Mr. Sutton here, bringing you the BC Calculus 7-8 Extra Practice number 5 solutions on interval of convergence. To find the radius of convergence on this problem, since it's not a geometric series, we need to use the ratio test. So I've got the limit as n approaches infinity of the absolute value of, and now we need the n plus 1th version of this over the nth term. So up top we're going to have n plus 1 times x to the n plus 1 over 4 to the n plus 1. And in here, we're going to have n plus 1 squared plus 1, which is going to be kind of crazy to look at. Down below now we just have the nth term, so just basically the sum and written as it is. And now let's do a same change flip to simplify this a little bit. So in the numerator, I'm going to have n plus 1 times x to the n plus 1 times this 4 to the n and n squared plus 1. So all those four things written in whatever order you want. And down below, we've got 4 to the n plus 1. This stuff, let's see here, this is n squared plus 2n plus 1 plus another 1. So that's n squared plus 2n plus 2. And we also have this n times x to the n. So a bunch of stuff down below. Time to simplify a little bit more. These 4's here can reduce to give me just a 4 to the first power in the denominator. And these x's can also reduce. So we have x to the n plus 1 divided by x to the n. That cancels out pretty much everything except an x in the numerator. So in the numerator, that 4 was gone. We still have the n squared plus 1. We have an n plus 1. And we have this x to the, just x actually, no exponent now. Or an exponent of 1 if we're really being technical. Down below, we've still got an n. This x to the n is gone. We have just a 4, so a 4 and an n, and all that stuff in parentheses. And now as n approaches infinity, I can forget about that plus 1 in there and also that other plus 1. And I can forget about the plus 2n plus 2 in this parentheses. These slower growing terms can be ignored as we go to infinity. So I essentially just have x n cubed in the numerator. Down below I've got 4 n cubed. So n cubes are going to cancel. We just end up with x over 4 in absolute value. And now in order for this series to converge, I need for this nth ratio to be less than 1. And to get the radius of convergence, I need x to have a coefficient of 1. So instead of writing 1/4 x, I want to just write x in here. So to do that, I'm going to multiply everything by 4. So that gives me absolute value of x less than 4. Which means the radius of convergence is going to be whatever's over on the other side at this point when x has a coefficient of 1. So that's a radius of convergence of 4. For this problem, we want to know which of these is the radius of convergence for this series. Since this is not geometric, I'm going to have to use the ratio test to find the radius of convergence. So I have the limit as n approaches infinity, absolute value of n plus 1th version of this. So 2x minus 3 to the n plus 1 over n plus 1. All of that over the nth term. So basically finding the nth ratio, as it were. So that's just going to be the 2x minus 3 to the n over n that you see in the sum and. And now same change flip. We've got 2x minus 3 to the n plus 1 times n in the numerator. Denominator, we have the n plus 1 and we have the 2x minus 3 to the n. We can reduce these 2x minus 3's. So that'll just give me a single 2x minus 3 in the numerator. We also have an n up there still. And down below there's nothing but this n plus 1. As n approaches infinity, we can forget about this slower growing plus 1 in the denominator. So you have 2x minus 3n over n. N's cancel, leaving us with just 2x minus 3 in absolute value. And now for the series to converge, this ratio needs to be less than 1. And to get the radius of convergence, which is really what they wanted here, I need this x in this absolute value to have a coefficient of 1. So to get that, I simply have to divide everything by 2. So that'll give me absolute value of x minus 3/2 less than 1/2. And then the radius of convergence is just whatever's on the other side when you have that coefficient of 1. So that's just going to be 1/2, which is answer choice C. To find the interval of convergence on this, since it's not a geometric series, we have to use the ratio test. So have limit as n approaches infinity, absolute value of n plus 1th version of this, so n plus 1 factorial times x minus 4 to the n plus 1, all of that, over the nth term, which is just n factorial x minus 4 to the n. We can reduce a few things. These factorials reduce to just give me an n plus 1 in the numerator, and these x minus 4s reduce to give me just a single x minus 4 in the numerator. So as n approaches infinity, this whole thing is growing to infinity. Now, since this interval converges if the ratio is less than 1 and infinity is clearly greater than 1, this doesn't converge a whole lot. The only thing that is going to make this converge is if you zero out the whole sum by making x4 basically the center of the series. We always get that for free. So I guess our interval of convergence then is just going to be x equals 4, and that's it. To find the interval of convergence for this series, it would help if we had a good expression for the nth term, because this is not geometric, so we are going to have to use the ratio test. So it looks like we have an x plus 1 to the n power over n factorial, and we also have a negative 1 to the nth power, but that's not going to matter if we're using the ratio test. So let's have the limit then, as n approaches infinity, of the n plus 1th version of everything going on. So that would be x plus 1 to the n plus 1 over n plus 1 factorial. And now the nth term that we were just talking about, that was x plus 1 to the n over n factorial. Same change flip, we have x plus 1 to the n plus 1 times n factorial in the numerator. Downstairs we've got n plus 1 factorial times x plus 1 to the n. These x plus 1s can reduce to give me a single x plus 1 in the numerator, and these factorials reduce to give me an n plus 1 in the denominator. So all that we have up top is the x plus 1, and all that we have on the bottom is the n plus 1. Now as n approaches infinity, only the denominator is growing, so this is a bottom-heavy function which goes to 0. And since this will converge for wherever we have a ratio that's less than 1 and 0 is always less than 1, that means this is going to converge for all x values. So we can say negative infinity less than x less than infinity for our interval of convergence. To find the interval of convergence here, it's helpful to notice that this is a geometric series with an r value of x plus 5. That means that to find interval of convergence, we just need the absolute value of our common ratio to be less than 1. And now we just have to solve for x. So I'm ready to rewrite this without the absolute value. We can write this as negative 1 less than x plus 5 less than 1. And then just subtracting 5 everywhere, we've got negative 6 less than x less than negative 4. Since this is a geometric series, that means that there's no ambiguity at the endpoints. They never get included in the interval of convergence for a geometric series. So this is going to be our final interval of convergence. On this problem, we're trying to figure out the interval of convergence for ln of x all to the n. So since this is a geometric series with a common ratio of ln of x, we can find the interval of convergence by just letting the absolute value of this r be less than 1. So writing that now, we just have to solve for x. I'm actually ready to rewrite this without the absolute value. We can just write negative 1 less than ln of x less than 1. And now solving for x, we have to raise all three of these spots here. We have to raise e to all three of these sides. So e to the negative 1, we can call that 1 over e if we want to really simplify it. That's going to give us an x in here if we raise e to the ln of x. And then this is going to be less than e to the 1, or just e. So 1 over e less than x less than e. And since this is a geometric series, that means there's no ambiguity at the endpoints. We don't have to test them. We never include endpoints for a geometric series. For this problem, we're looking for the interval of convergence for this series. And here's the general term. Now, one thing that's worth noting on here is that this is a geometric series. We have an r value of negative x squared for this. Since it's geometric, I can find the interval of convergence by just taking the absolute value of my common ratio and letting that be less than 1. So absolute value then of x squared, I don't have to write the negative if I've got the absolute value. And to solve for x here, we just square root both sides. So we have absolute value of x is less than 1, the square root of 1. And then I can just rewrite this without the absolute value as negative 1 less than x less than 1. Since this is geometric, the endpoints are never included in the interval of convergence, so we are done. For this problem, we're trying to find the radius and interval of convergence for this series. Since this is not geometric, we use the ratio test to determine this. So we'll have the limit as n approaches infinity of absolute value of, and now we have the n plus 1 over the nth term, so n plus 1 factorial x plus 1 to the n plus 1 over basically all of this stuff written as is downstairs, so because this is the nth term. Now we can reduce a little bit. N plus 1 factorial over n factorial. Well, since n plus 1 factorial is basically n plus 1 times n factorial, those reduce to just leave you with n plus 1. And using our exponent rules and subtracting the exponents, we end up with just x plus 1 to the first power if we reduce these. So when all is said and done, we have limit as n approaches infinity, absolute value of n plus 1 times x plus 1, which grows to infinity as n approaches infinity. Now, in order to converge, this series ratio needed to be less than 1. Infinity is not less than 1. It's, in fact, greater than 1. That means there's no way to set up one of those absolute value less than 1 expressions to find the radius of convergence. The radius of convergence on this is going to be 0. There is no radius of convergence. However, that doesn't mean that it doesn't converge anywhere. It means that you still converge at the center of the series. You're always guaranteed to converge at the center, which is going to be whatever zeroes out the series if you plug that number in for x. In this case, the center is going to be x equals negative 1. So we are going to converge at x equals negative 1 because if you zero out this term, that zeroes out the whole series, and then you're just adding a bunch of zeros over and over again, which is going to converge to 0. But that's about it. For this free response problem, we have this function defined with this series here, which if I wanted to, I could just write this as f of x equals the sum from 0 to infinity of basically the general term here. So either way. Now we want to find for part A the interval of convergence for this power series. Since this is not geometric, I have to use my ratio test. So I have limit as n approaches infinity of absolute value of n plus 1th version of this over the nth term. So that's going to be, for the n plus 1 of this, that's going to be n plus 1 plus 1, so n plus 2. We have an x to the n plus 1. We also have a 3 to the n plus 2. So that's all the n plus 1th term. And for the nth term that we're dividing that by, we just use the original summand here. So now, simplifying this, multiplying by the reciprocal, in the numerator we have n plus 2 times x to the n plus 1 times this 3 to the n plus 1. And down below we have 3 to the n plus 2, n plus 1, and x to the n. I can reduce this a little bit. These 3's are just going to reduce to give me a 3 down in the denominator. And these x's will reduce to give me an x in the numerator. Can't do anything yet with the n's. So upstairs now we have an n plus 2 and an x. Downstairs we have a 3 and an n plus 1. As n approaches infinity, I can ignore these slower growing plus 2 and plus 1 constants with my n's. So then I really just have xn over 3n. N's cancel, leaving me with just x over 3 in absolute value. And now for this series to converge, my nth ratio, which is this expression here that I just got, that has to have a value of less than 1 in order to guarantee that we converge. So solving for x here, just multiply by 3. We have absolute value of x less than 3. And I can rewrite that without the absolute value as negative 3 less than x less than 3, which is great as far as it goes. Unfortunately, because I used the ratio test to come up with this, we don't know about the endpoints. The endpoints may or may not actually be in the interval of convergence, so we have to test them individually. So let's test out x equals negative 3, or f of negative 3, basically the same thing. If I plug negative 3 into my series, what does that look like? Well, I've got, this is going in for x, so this is going to be, we have a negative 3 to the n, we have a 3 to the n plus 1, and I can actually make my life a little bit easier if I think of this as being like a 1/3 times this series with a 3 to the n inside. In that case, if I have negative 3 to the n over 3 to the n, that would be negative 1 to the n. So here's what the series looks like then. Again, I basically factored a 1/3 out of here so that I would have 3 to the n, and I could then combine the negative 3 to the n and the 3 to the n to give me negative 1 to the n. The rest of it's pretty much unchanged. Now I'm going to test this with my nth term test. I always do that first just to make sure that things will actually work out as n approaches infinity for the nth term. So the limit of this thing is going to be, well, let's see here. This thing is growing to infinity. We have this plus or minus kind of business going on with this -1 to the n. So I guess you could write plus or minus infinity. Either way, it's not 0. So this diverges by the nth term test, and we do not include -3 in our interval of convergence. Now let's test out f of positive 3. So doing the same thing, pulling out this 1/3, we essentially have 1/3, and then we have 3 to the n over 3 to the n, which is just 1. So we just end up with then 1/3 times n plus 1. As n goes to infinity for this expression, doing our nth term test, this just grows to positive infinity, which is still not 0. So this one also diverges by the nth term test. And then that means that neither of these endpoints are included. So for our final interval of convergence, we write -3 less than x less than 3. For this part of the problem, they want us to find the limit as x approaches 0 of all of this stuff here. So you can see if you just try plugging 0 in for x, I mean right away we're going to have 0 in the denominator, so that's already not so good. If we do f of 0 up here, that zeroes out everything except for this 1/3. So you would end up with 1/3 minus 1/3, which is also bad news because then you end up with 0 over 0, and we all know that the indeterminate form is not an acceptable final answer for limits. So what are we going to do here? Well, you could try using L'Hopital's, but then you've got to take the derivative of all this stuff, which may not be as fun as it sounds at first glance, because it's an infinite series. So another way to do this is, let me just do a little transformation with this series. Since we have f of x minus 1/3 as the numerator here, let's just talk about that by itself. F of x minus 1/3, that's really all of this stuff without this 1/3 in here. So it's really just 2 over 3 squared x plus 3 over 3 cubed x squared and all the rest of that stuff. And now just to take our transformation one step further, we've got, let's see here, all this stuff divided by x. So that's just going to be 2 over 3 squared with no x there. Plus now we've got 3 over 3 cubed x and all the rest of these. This will eventually be an x to the n minus 1. So there's 2 over 3 squared, 3 over 3 cubed x, n plus 1 over 3 to the n plus 1, and the only change is we have n minus 1 for that exponent. So we're getting there. There's only one other thing that we need to do, and that is to take the limit as x approaches 0 of all of that stuff. Well, if we take this expression that we just wrote here and plug in 0 for x, at this point, since we just have x as the numerator basically in a bunch of terms, all these terms with x's are going to go away. They're going to get zeroed out. The only thing that's going to be left is this constant 2 over 3 squared that we see in the beginning. And you can leave it like that. You could write it as 2 over 9 if you want to be fancy. Either way, though, that's our limit. For this part, they just want the first 3 non-zero terms in general term for an infinite series representing integral from 0 to 1 of f of x dx. So basically, let's just use the fundamental theorem on this function here and take some antiderivatives. So our antiderivative of our first term, 1/3, that's going to be 1/3 x. And then for the next one, this is going to be, let's see, this bumps up to x squared. Dividing by 2, we just have 1 over 3 squared times x squared. So 1 over 9x squared. For this next thing, our exponent bumps up to a 3. Dividing by that, we have 1 over 27x cubed. And just for the general term now, this bumps up to an n plus 1. Dividing by that, the n plus 1s conveniently cancel. So we just have 1 over 3 to the n plus 1 times x to the n plus 1. And we'll do a plus dot dot dot. All of this is now being evaluated from 0 to 1. Okay, well, if I plug 1 into all of that stuff, since we've really just got an x squared or an x cubed or an x to whatever power next to each of these coefficients, and you're just plugging 1 in, you're just going to end up getting whatever the coefficient is. So this first thing is going to be 1/3 plus 1/9 plus 1 over 27 plus over here, just 1 over 3 to the n plus 1. So really just keeping those coefficients. Now if we subtract all of this stuff with 0 plugged in, well, hold on a sec. Since everything here is being multiplied by an x, plugging 0 in for x is just going to zero out everything. So really you'd be subtracting 0, which there's no point in writing. So what we've written here is actually done. For the final part of this problem, they want us to find the sum of the series determined in part C. So here was that series again. Now, often when they ask us for the sum of a series, an infinite series, very often it turns out to be a geometric series, and in this case it certainly is. We have an A1 value, so this is geometric. We have an A1 value of 1/3. We have a common ratio, an R value of, let's see, I'm multiplying by 1/3 to get each of these things. So just using my infinite sum formula, we have A1 over 1 minus R in general. So that's going to be 1/3 over 1 minus 1/3. And we could leave it like that, but if you wanted to simplify, this is 1/3 over 2/3. And then we've got same change flip here. We have 1/3 times 3 halves. 3's cancel. We end up with just 1/2. And that's as good as it gets.